Welcome back. Now let's talk about this pH scale. One of the characteristics of an acid and a base is what its pH of that solution might be. So as you can see from this visual, acids have a low pH number, bases have a high pH number. Now what we're going to see is that this pH is a logarithmic scale because what you're measuring is the concentration of hydrogen ions, which is why this nice little picture is right there. It's a little cumbersome to talk in terms of concentrations of ions in a solution. So pH is a much easier way to kind of wrap your brain around that. So in this case, the logarithmic scale is a good thing for us. Now what you might not have used before is the pOH scale. Now the pOH scale is exactly like the pH scale, but instead of measuring hydrogen ions, the pOH scale will measure hydroxide ions. So if you have a solution that is predominantly basic, then we're going to be using the pOH scale. And it kind of looks exactly the same. It goes from 0 to 14, but in the pOH world, everything is flipped. So if we wrote kind of off to the side over here, you would have acids kind of having high pOH numbers and bases having low pOH numbers. So they kind of go the other direction. Okay, how do we calculate pH? So pH, again, it's a logarithmic scale and is a measurement of ions. So we need to know what is the concentration of either the proton or the OH in each one of our scenarios. So how do we do this? Well, pH is equal to the negative log of your concentration of hydrogen ions. So if you know your concentration of hydrogen ions, you can figure out your pH. pOH, same sort of idea, but instead of hydrogen ions, we're going to be measuring hydroxide ions. And I was just about to write a positive charge on my hydroxides, and that's wrong. So here we go, hydroxides. Okay, so you're going to take the negative log of your concentration. Now remember, these brackets mean molarity. So concentration is going to be measured in molarity. Now if you know your pH, you can figure out your pOH, because if you add them together, you get 14. And if you jump back and you take a look at the pH scale, you can kind of see why that works. On the flip side, if you know your pH, you can figure out your concentration of hydrogen ions. All you need to do is take the anti-log. So we call this the anti-log. You do 10 to the negative on your calculator. It's usually right above the log button. If you're not sure how to do that on your calculator, just come see me. And same sort of thing over here. If you know your pOH, you can then calculate the concentration of hydroxide ions by doing the anti-log. Now the other thing that is handy, and we'll kind of come down the road, there's many things that are on this logarithmic scale, not just pH and pOH, but if you remember, Kw was our equilibrium constant for water, and it's 1 times 10 to the negative 14th. People don't like exponents, so if you take the negative log of that, it actually equals 14. So if your pH plus your pOH equals your pKw, which is 14. So now let's do some practice with it. Alright, calculate the pH of a 0.1 molar nitric acid solution. So the first question we're going to ask ourselves is, what is nitric acid? Is it a strong acid or is it a weak acid? Well, from your list of 7, we know that nitric acid is a strong acid, which means you really don't have HNO3. What you have is a concentration of hydrogen ions and a concentration of nitrate ions. So it completely dissociates, which means if I know my molarity, which I do here, that means that I know my concentration of hydrogen ions. So with a strong acid, your concentration of hydrogen ions is your molarity. So remember that those brackets mean molarity. So once I know the molarity, once I know my concentration of hydrogen ions, to calculate pH, all I gotta do is take the negative log of my concentration of hydrogen ions, which in this case is 0.01. Plug that into your calculator. You do negative log 0.10. Sorry, I think I said it backwards. And you come up with a pH of 1. Now when you do these pH and pOH calculations, always ask yourself, does this answer make sense? This is an acid. I would expect a pH to have a low number. Second example, calculate the pH of a 0.5 molar solution of potassium hydroxide. So the first question you're going to ask yourself, is this a strong base or a weak base? Potassium hydroxide is ending in an OH, so I know it's a base. This is a strong base because it's made from an alkali metal. So what that means is that I really don't have potassium hydroxide. What I have is a concentration of potassium ions and hydroxide ions. Well, in both of the first example and this example, it's not the nitrate that's important. It's not the potassium that's important, because those aren't things that affect pH. pH is a measure of hydrogen ions. pOH is a measure of hydroxide ions. So I really don't care about these little spectator ions. What I care about is my concentration of hydrogens or hydroxides. So in this particular case, what do I know? Well, I know my molarity, but I don't know my molarity of hydrogen ions. I know molarity of hydroxide ions. And the molarity of my hydroxide ions is 0.5. So given hydroxides, I can't solve for pH, but I can solve for pOH, because pOH is the negative log of my concentration of hydroxide ions. So all I gotta do here is take the negative log of 0.050, and that's going to give me a pOH of 0.301. Now I'm not quite done yet, because the problem says calculate the pH. So here I'm going to go back and use the relationship that pH plus pOH equals 14. And so since I know my pOH, to figure out my pH, let me write that in here, pH equals 14. Let me write it so actually you can read that. pH equals 14 minus 0.301, which is 13.7. And again, ask yourself, does my answer make sense? This is a base. I would expect a pH to have a really high number. Third example, the pH of blood is 7.4. 1. Calculate your concentration of hydrogen ions and hydroxide ions. So even though something is an acid or a base, doesn't mean that it only has hydrogen ions or it only has hydroxide ions, because remember, these are aqueous solutions and water auto-ionizes. So whether it's acidic or basic, you still have concentrations of the other ion in there. It's just that one predominates over the other. So I pull out this example because if you know your pH, we could figure out our concentrations. How can we do that, you might ask? Well, because of this little relationship. If you know your pH, and if you do 10 to the negative pH, that's going to equal your concentration of hydrogen ions. So to get to my hydrogen ions, I'm going to do 10 to the negative 0.741. This is the antilog. So now this gives me my concentration of hydrogen ions. So 10 to the negative 7.41. So take 10 to the negative 7.1 against that's the antilog button, and that comes up with your concentration of hydrogen ions of being 3.89 times 10 to the negative 8th. Don't forget that little exponent thing on your calculator. These should be tiny numbers. So if you come up with 3.89, you're saying that there's only 3.89 hydrogen ions. That doesn't make sense. So don't forget your little exponent piece. Now the other part of this problem says calculate your hydroxide ions. So how are you going to do this? Well, you could do this in a couple different ways. If you know that hydrogen ions times your hydroxide ions equals your Kw, and you can approach it from that way. Or you can approach it from this direction of, since you know your pH, you can figure out your pOH, because 14 minus your pH gives you a pOH of 6.59. And then your concentration of hydroxide ions is going to be 10 to the negative pOH. So if I do 10 to the negative 6.59, that will give me 2.57 times 10 to the negative 7th. And again, this is equal to your concentration of hydroxide ions. And again, don't forget that lovely little exponent piece, because that is important. Okay. Now those are pretty easy, because those are for strong acids and strong bases. Where it gets a little bit more complex is when we start talking about weak acids and weak bases. So what I've given you here, and your textbook goes through these as well. These are just some strategies of how to go about solving these more complex questions. Now, some are going to be more complex than others, so what we're going to be practicing here is a problem-solving strategy. So some of the steps are going to seem really easy, and you're going to wonder, why are we doing these? Trust me, the more complicated they get, you will have this problem-solving strategy kind of fall back on. All right, list major species in solution. So in other words, you're remembering that all these things are dissolved in water. Whether you're talking about an acid or a base, everything is in water. Look for reactions that can be assumed to go to completion. So that would be your strong acids, strong bases, because those are going to be, the math problems that we just kind of went over. For a reaction that can be assumed to go to completion, determine your concentration, write down the major species of the solution after reaction, so that's using your molarity. Look at each major component of the solution and decide whether it's an acid or a base. So are you looking for hydrogen ions or are you looking for hydroxide ions? Step 5. Pick the equilibrium that will control the pH. So if you have things that are not strong, things are weak, you got to look for things that are going to directly affect the pH. So look for those hydrogens and hydroxides. Write your equation for the reaction and the equilibrium expression. So this is going to be either your Ka or your Kb, depending on what you're talking about. So always kind of write out your equilibrium expression. Figure out your initial concentrations, assuming that it's not strong. In other words, these steps right here are going to be your ice box. You're going to come up with your ice calculations. Define X. Substitute the equilibrium concentrations in for X. I should extend this on down. And these are your icebox techniques that you learned in the previous chapter. Substitute concentrations into the equilibrium expression, solve for X. There's a little shortcut that we talked about in the previous chapter. With this one, you're going to have to just kind of check and make sure that your assumption, that little shortcut, is correct. And then from there, calculate the pH or whatever else the problem is asking you. So what this is kind of teaching you to do is, I don't want you to memorize a bunch of stuff. I want you to really think about the chemistry, and this is where it gets complex. You have to be able to think about the equation that's happening and then use a systematic approach to solving these. Don't try to memorize, oh, I have to do this for this particular case and that for that particular case. You have to be flexible and you have to think about it and approach it step by step. So let's begin doing some practice problems. What is the pH of 25 milliliters of a 0.25 molar solution of acetic acid? So first of all, let's think about what the substance is that we're working on. Well, this is acetic acid. Is it strong or is it weak? Hopefully in your head, you're going, it's weak, because why would I be doing this for a strong acid? It is a weak acid, which means it exists in a state of equilibrium. Okay, so I'm going to write out the dissociation equation and the species that are involved. In a few steps here, I'm also going to be writing out my equilibrium expression. So in this case, my equilibrium expression is going to be a Ka, because we're talking about an acid. Okay, now what I'm going to do is I'm going to calculate my initial concentrations. I'm going to calculate my change and my equilibrium. So that's where my icebox comes in. 0.25 molar solution of acetic acid. Now what does the 25 milliliters have to do with it? In this particular case, nothing. It just means you've sucked up 25 milliliters of a 0.25 molar solution of acetic acid. So my initial concentration here is going to be 0.25 molar. Okay. For this case, I'm going to keep everything in concentration. Other cases, I'm going to flip out of it and you'll see why. What's my initial concentration of hydrogen? My initial concentration of acetate ions, 0 and 0. Why? Because nothing's happened yet. This is my initial concentration. Now once things come to equilibrium, I know it's going to change. My initial concentration can only go down. My product concentrations can only go up. So it's going to change by negative X and positive X. So at equilibrium, oops, pen kind of paused there. So at equilibrium, my concentration of the acetic acid is 0.250 minus X. This is X, and this is X. Now I'm going to set up my Ka expression. So Ka, products over reactants. Okay, put my reactant in the bottom there. Oh, I forgot my little subscript. Okay. Now plug in the values that you've gleaned from your icebox. So we've got x times x, 0.250 minus x. Now what is my k equal to? Well, this is the additional piece of information. Either you're going to have to look it up or it's given to you in the problem. Here is the Ka value for acetic acid. I knew there was a reason I had that little table off to the side. So my equilibrium constant value is 1.8 times 10 to the negative fifth. Now here's what we're going to do. We're going to make a little assumption, and this is a little shortcut that we can use. We can reasonably say, based on the fact that the Ka value is really tiny, 1.8 times 10 to the negative fifth, I can pretty much assume that any change that this is going to do is negligible. So I can eliminate the x in the denominator, which makes solving for x so much easier. So now we've got x squared over 0.25 equals 1.8 times 10 to the negative fifth. So then you go through and you solve for x, and x comes out to be 0.00211. Okay? Now how is that a legal assumption? Well, if you look at my value for x, remember that x was my change. How did concentrations change? Well, this is less than 1% of my initial concentration up here. So yeah, it was pretty reasonable to say that my change in concentration was negligible, so I could ignore that x in the denominator. Now, what is the other thing that x means? What did this give me? Well, if we come back up here to my icebox, x is my concentration of hydrogen ions. There is what x means. X is my concentration of hydrogen ions. And if I think about what I need to solve for pH, to calculate pH, I'm going to take the negative log of my concentration of hydrogen ions, which means now that I've solved for x, I'm going to do the negative log of 0.00211, and my pH is 2.68. Now, logarithmic scales have slightly different sig fig rules. My general thumb is I leave 2 decimal places in there and you're good to go. Does my answer make sense? Yes, this is an appropriate pH value for an acid. All right, what if we have percent dissociation? So back here, I talked a little bit about why this shortcut was legal, and it has to do with the idea of dissociation. To what extent does the acetic acid dissociate into hydrogen ions and acetate ions? And we can kind of tell by looking at this particular answer that it is less than 1%. But we need to be able to calculate that, so let's do a practice percent dissociation. Now, formic acid. Of course, you've got the formula for formic acid just sitting in your head. Right there. It's actually also called methanoic acid, which when you take organic chemistry, that'll make a whole lot more sense why. But the first thing that you're always going to do is set up your ICE table from this, because when you're figuring out percent dissociation, you're trying to say, well, how did my concentrations change? Initial, well, that's my starting molarity, 0.325 molar. My initial concentration of hydrogen ions is 0. The formic acid ion is 0. How is this going to change? I don't know. I'm going to have to figure that out, but I do know that products go up, reactants go down. So at equilibrium, my concentration is 0.325x, or 0.325 minus x, and hydrogens are at x and x. From here, set up your Ka expression. A is for acids. So, whoops. There we go. So I got my Ka expression. I can tell from the table, the previous table over here. Nope, it's not on there. My mistake. Okay. Well, I'm just going to tell you what it is. It is 1.8 times 10 to the negative fourth. There's a much more comprehensive table in your textbook, or the problem will have that included, so don't worry about where you're supposed to get that number from. You'll be able to find it pretty easily. Now let's substitute in our values from our icebox. So we've got x times x divided by 325 minus x equals 1.8 times 10 to the negative fourth. So now here what we're going to do is make that little assumption that this x down here is negligible, is so tiny that we don't even really care about it, which makes our solving for x really easy. And x equals 0.00756. Okay, so now I know what my concentrations are. And again, think about your icebox, and that's why these are so dang handy, is because it helps you realize what does x mean, what does x represent. So now let's calculate percent dissociation from that. Now percent dissociation is just like percent of anything. You take the smaller piece, or the smaller number that goes on the top, in other words the part that you're wondering about, the amount of ions that you've created, so in this case the value for x, and I'm going to compare that to the total, or what I started with. So here's what I started with, here's what I ended with. We do that, multiply it by 100, and this dissociated less than 2.3, or somewhere around 2.33%. Okay, which also helps us figure out, yes, our little shortcut was indeed valid because it's less than 5% of your original concentration. General rule of thumb, if your percent dissociation is greater than 5%, then you can't really do this little sneaky maneuver right here because the change actually does have an effect. But good news for AP, you don't have to worry about that. Okay, last thing that we're going to talk about with calculating pH is how do you calculate the pH for a weak base. Now here's where it gets a little bit more complex, and you got to stick with your rules and your steps. First step is you got to write out your equilibrium. Well, we know this is a weak base because it's not made with an alkali metal or with one of the 3 alkaline earth metals. And here's where it's kind of handy to write in water, because these are in aqueous solutions, and it helps us see the equilibrium and where we're going to get the species that affects the equilibrium, namely the hydroxide ions. Okay, so we're going to write our equation, start setting up our icebox, and think about what we have here. My initial concentration of ammonia is 0.25. Now for water, remember that water is liquid. I'll draw a nice little box here. The water is liquid. Really, I don't care what the water is because we don't include liquids in a Ka or a Kb or a K anything expression. So really, I'm just going to leave that blank. My initial concentration of ammonium is 0. Hydroxide is 0. Change x, x. It's going to go down by x, go up by x. At equilibrium, 0.25 minus x, x, x. Okay. Next step, set up your Kb expression. Products over reactants. Remember that Kb is just an equilibrium expression, but used for bases. The B just means base. Now, like with everything else, we have to figure out what is our value for Kb, and so there's going to be some nice little table. Here it is right there. So I know that Kb is equal to 1.8 times 10 to the negative fifth. So again, this is probably going to be some information that you either look up in a really big table or it's given to you in the problem. Now let's substitute in our values from our icebox. So we've got x times x divided by 0.25 minus x equals 1.8 times 10 to the negative fifth. Now this is a really tiny number, 1.8 times 10 to the negative fifth. Remember that when you have the value for equilibrium constant, it gives you a sense of whether the products are favored or reactants are favored. Numbers less than 1 tell you that the reactants are favored. So this is dissociating, but not that much. So since this is a little tiny number, we can take the same shortcut as we did with the acids. Oops, that should be a 5. Why is it not a 5? 0.25. Sorry about that, guys. X squared over 0.25 equals 1.8 times 10 to the negative fifth. And I go through and I solve for x, and it comes out to be 0.00211. Yay! Now before you go, I'm done! Just go back and look what the problem was. What is the pH? Now for pH, remember what you need for pH. pH, you're going to take the negative log of your concentration of hydrogen ions. Do I have hydrogen ions? Nope, because X is hydroxide ions. So I can't figure out pH directly from hydroxide. What I can figure out though is my pOH. So since I know my concentration of hydroxide ions, I'm going to take the negative log of your X value, what you just figured out, and that's going to give me a pOH of 2.68. Now at this point, guys, if you forgot this little step, but you're in the habit of asking yourself, does my answer make sense? And you're like, oh, pH is 2.68. Hey, wait a second, it's ammonia. That's a base. That doesn't make sense. That's because what you really figured out was your pOH. To get to pH, once you've got your pOH, subtract it from 14. So the pH of a 0.25 molar solution of ammonia is 11.32. And that should make more sense. Okay, last thing that we're going to talk about in terms of dissociation. What happens if you've got what we call polyprotic acids? So all the acids that we've dealt with, whether it's formic acid or acetic acid or hydrochloric acid or anything like that, so far they've all been monoprotic. They just have one hydrogen. So that's what we mean by monoprotic. So if you've got a monoprotic acid, it's just going to dissociate that one hydrogen. Well, the thing about acids is that they dissociate one hydrogen at a time. So let's say, for instance, you have sulfuric acid. This is a diprotic acid. It's got two hydrogens, but it dissociates one hydrogen at a time. So it actually has two separate dissociations, where the first hydrogen pops off, oops, and then the second hydrogen pops off. So sulfuric acid is one of our strong acids. So this first dissociation, we're going to kind of basically completely dissociate, but notice that it leaves this conjugate base here, this HSO4. Conjugate base, the weak conjugate base of a strong acid. But then this HSO4, it is a weak acid, it is no longer a strong acid, so it's actually found more in equilibrium. My arrows are not so good today. But it will dissociate that second hydrogen. What that means is that we will have different Ka expressions. You can have a Ka1 and you can have a Ka2. Now if it's a triprotic acid, for instance phosphoric acid, that means you're going to have three hydrogens to dissociate. Now phosphoric acid is a weak acid, so from the get-go it is also going to be in equilibrium. But what I want to show you is what is left as each hydrogen pops off. Because the more we get into these things, the more you'll have to keep that piece in mind, that you're going to have these other species that come about. Okay. Since this is triprotic and we get three different reactions that take place, that means, ooh, where did it go? Technical difficulties. That means that you're actually going to have three separate Ka values. That's Ka2. And you can write three different Ka expressions. So like the Ka for this one would be H+, the hydrogen sulfate ion over sulfuric acid. And this one would be H+, the sulfate ion over the hydrogen sulfate ion. Okay. Now each one of these K expressions has a different value. So my other purpose for showing you these things about the acids, other than to realize why acids dissociate one thing at a time, is to show you that, yep, sulfuric acid is a strong acid. The Ka1 is incredibly large, which is why we reasonably say that it completely dissociates. So when we're calculating pH for sulfuric acid, really you only need to worry about this one. You don't have to do an icebox table or anything for sulfuric acid. Whatever your molarity of the hydrogen ions is, you're going to use that for your pH. But notice for phosphoric acid how the Ka's drastically drop as you go from one hydrogen to another. What this is telling you is by the time you hit that second and third hydrogen, it is popping off so little that it's really not going to affect the pH much. You won't really see this too much with AP having to, but you could go through and calculate the pH for this whole particular thing, but you'd have to do 3 separate calculations for the Ka. But this is the main idea, that these Ka2 and Ka3 we don't normally work with as much because they're not contributing to the overall pH of the solution. Alright, up next we will talk about acids, bases, and salts.